Good morning, guys. I guess we're afternoon now. I am going to complete this circuit that I gave you last class at the end of the day, and we're going to work our way through it. So if we look on here, we have 120 volts as our supply voltage. When we go out into the line, we see that there's two coils that produce the line voltage, and they're not 180 degrees out of phase with each other, they're 120. So we know that, our line voltage is root 3 larger. So 120 times root 3 gives us a value of 208 volts for our line voltage. So we've got 120 volts in phase number 1, our phase 1 of our supply. In load number 1, that line voltage, 208 volts, when we go to come into the load, there's only one load that sees that 208 volts. It's not two, so we wouldn't be splitting it like we would in Y. So we know that there's 208 volts dropped across that delta load. As we know, rule for voltages in delta, that the line and the phase are both the same, so we get 208 volts. Then we come over to our Y configuration, and we know that our 208 volts in Y gets split between two phases, so we are root 3 smaller. But then also the rule that you know is that anytime you have a supply that's in Y and you have a load in Y, the phase values are the same. So we know that this is 120 volts. We have a resistive value of 6 ohms in load number 2 and 5 ohms in load number 1. If we look at 120 volts and 6 ohms and use Ohm's law and look at the current as being E divided by R, we take our 120 volts divided by 6, and that gives us an answer of 20 amps. So 120 volts divided by 6 ohms is 20 amps. All right? And if we continue on with that and we want to look at our three-phase power, we've got a formula for three-phase power as our E phase times I phase times 3 gives us our three-phase power. So 120 volts times 20 times 3 gives us our three-phase power. So 120 times 20 times 3 gives us a total power of 7.2 kilowatts. Just going to erase this here. So 120 times 20 times 3 gives us our answer of 7.2 kilowatts. Now let's move over to the next load. We've got 208 volts and 5 ohms. And if we take 208 volts divided by 5, we get an answer of 41.6 amps. So we know that that 41.6 amps goes right there. And if we use this formula here for finding three-phase power, 208 volts times 41.6 times 3 gives us an answer of 33 point, that's the final one. Gives us an answer of 25.958 kilowatts. Okay? So in order to find that, I'll just write it out as well, just so you see. 208 times 41.6 times 3 gives us 25.958 kilowatts. And from what we had talked about last class, you can go through this formula several different ways. The easiest, as you guys had seen, was to add up all your powers and find your total power and then find the current that way. And if you add up your two powers, you get 25.958 plus 7.2. That gives you, and this was the number I was writing down before, 33.158 kilowatts. And from there, you can take that value divided by 120 times 3, and it'll give you what the total current is. And the way I found that was the formula that we had looked at was, or the formula to calculate it would have been 120 volts, which was our E phase, times our I phase, which we don't know, times 3, and our total power that we calculated is 33.158, and we want to isolate our I phase by itself, so we would just divide both sides by the same thing. So we divide 120 times 3 and 120 times 3, and all that would cross itself out. So we get 33.158 kilowatts divided by basically 360. And if we calculate that, we get a number of 92.11, or let's round to 3 decimals. 92.106 amps. And for those who like also to do it or want to see it being done the other way as well, if we went to take an amp clamp and put an amp clamp on there, we saw 20 amps. We come onto line, means that it's also 20 amps. So we have a line current of 20 amps in Y, and as Y formula indicates that the current in the line and the current in the phase are the same. Now we're going to come over to our I phase in delta, and we had 41.6 amps. So that phase uses 41.6 amps, this phase uses 41.6 amps, and they're obviously not in phase with each other. They're 120 degrees out of phase, so the value is going to be root 3 larger. So if I take my 41.6 times 1.732, or root 3, I get a value of 72.05 amps. And there is some rounding going on here, so you see that the decimal is a little different. And if we then take the 72.05 and the 20 amps and we add those two together, 72.05 plus 20 gives us about 92 amps. And you see that our total current is 92.106. So this was actually 72.051. And there would have been some other decimals added in, or some rounding that came from here that put this one up a little bit higher. But other than that, you can see that they are close. One thing you will find when I'm doing tests is I don't care as much about rounding at the end of the day. If your number ends up being, if it's a large number and it's within, for instance, let's say 41.6, if it's anywhere from 41.2 to 41.8, error either way, or 5% error either way. So I'm not too much of a stickler on that. It's more if I know you can answer the question properly is what I more care about, not so much whether or not you can round. So, but that should get that answer finished for you. Hopefully you were able to figure that out. I'm going to move on and add a couple other formulas, and what I'd like to add right now is an inductive load into the circuit. But we need to look at our formulas for when there's an inductive load or a capacitive load, and then how those factor into the equation. One thing you have to look at is for power, our power formula. So P is equal to E phase times I phase times 3, and that was for true power. Anytime you have a reactive power, right? Reactive power is if you have a capacitive or inductive load. I'll just move it over. I'll just write it as RT, reactive power, and true power we know is measured in watts. When we have a reactive power, that's going to be measured in VARs. So it'll be VARs L or VARs C, and that formula is still E phase times I phase times 3. And it's the same if you're using line values. If you're using line values, this would be E line times I line times root 3. And then if we look at one other formula, I'll just give it to you now. If you have a combination of an inductive value or capacitive value with a resistive value, we know that that is now apparent power, and that's measured in volt amps. And the formula for that is VA is equal to E phase times I phase times 3 times our power factor. So we have to look at the power factor in that specific case. And in looking at power factor, if you remember, power factor is equal to our true power over apparent power, or just written as true power over apparent power. So those are some additional formulas you would need to remember, and then there also is the variation of the E line times I line times root 3 times our power factor. So make sure you commit those into memory. So I'm going to start off with having a capacitive and inductive value. If you just solely have an inductive value, the calculation is going to be the exact same way you would do it if you had a resistive value with the load. I'm just going to show you this with an inductive value. So we're going to do a delta supply. So we have a delta supply, and we're going to do a Y load. And this is going to be with an inductor. And let's do, actually let me make that a little smaller so I can fit more stuff in here. And we're going to do inductive Y load, and we're going to do a capacitive delta load on this side. Okay, so obviously those all get connected. In some manner or another. As long as they're all connected, you're good. So we're going to start this out with 208 volts to make it simple. And we're going to have E phase, I phase, and our VARs. C or L, and then when we go to do it, I'll indicate which one it is. Now we have load 1, which we know is inductive, and let's do this as 8 ohms. And our capacitor of 6 ohms of capacitance. We're going to have E phase, I phase, and we're going to have our resistance, but it's going to be our inductive reactance. So inductive reactance, and we're going to have capacitive reactance over here, which is going to be 6 ohms. This one's 8 ohms. Because we have 208 volts in our delta, when we go to look at that value in Y, we know that there's 2 loads seeing the 208 volts, so it makes it root 3 smaller. So we know that we have a phase voltage in our Y connected inductive load of 120 volts. Load number 2, which is capacitive. It's also in delta, so we know that anytime we have supply in delta, the load in delta is going to have the same voltage, and it's also going to be the same as what our line voltage is, which is 208 volts, because there's only one coil that produces that voltage, so 208 volts. So E phase is 208 volts. So power, which is in VARs, we can write. I guess you could write power and then put VARs at the end. But we have our 208 volts. So if we use Ohm's law again, fairly straightforward. Our I phase is equal to 208 volts divided by 6 ohms, gives us our current. So 208 divided by 6 gives us 34.667 amps. Now we're going to look at our current and our Y. We have 120 volts. So this is for load number 2, or load number 1, sorry. We have 120 volts divided by 8 ohms, and we get a current of 15 amps. So I'll just write that as our power. I'll change that around, sorry. Okay. So now we go to calculate our powers the exact same way as we would before, because we're not using a power factor in this case. So our power is equal to, or our reactive power is equal to 120 times 15 times 3. So 120 times times 15 times 3 gives us 5.4 kilovars, and that's going to be inductive. Kilovars. And we look at load number 2. Load number 2 is going to be 208 volts times 34.667 times 3. So 208 times 34.667 times 3. And we get a total capacitive vars of 21.632 kVars, and that is capacitive. I know it's kind of run out the board there. Sorry if you can't see that. Okay, so that's all your currents figured out, and that's all your powers figured out. The interesting thing with this is, and if you remember in doing your parallel RLC circuits and your series RLC circuits, that anytime you have a capacitive value and inductive value, you can't just add the two values together. Well, in this case, technically you can, but they don't add together the same way the resistive values did. But if we go and look at these, we need to put them, and we need to graph them. Let me see if I can get my big head out of the way here. And we need to graph them. And if you remember, this is resistive, and because it's in parallel, our inductive value is down here, and our capacitive value is here. So let's look at our currents. So everything that you can plot in a three-phase RL, RC, or RLC circuit is you can plot your currents and you can plot your powers just like you would in your regular series and single phase regular series and parallel circuits. So our capacitive value is for current is up here at 34.667 amps, and our current for our inductive load is 15 amps. And so that 15 amps is going to be subtracted from the 34 amps. It's the difference between the two of them. So 34.667 subtract 15, and we get a total current of, and I just did a brain fart there. Sorry, forget I put that in there. Can't use this value here, my bad. Anytime you're calculating these, and I do apologize, you need to use line values, not phase values. I do apologize for that. So 34.667 times root 3, because there's two capacitive loads that use that up, so we multiply it by 1.732 or root 3, and we get 60.04. 60.04 as our line current. However, this one, because it's in Y, it's the same, current is the same in the line as it is in the phase. So this one just has to change to 60.04. Hopefully you don't chastise me too much for making that mistake. So we have 60.04 and 15 amps, so 60.04 subtract 15, so we get a total of 45.04 amps seen at our load, and this was 208 volts. Now I want to show you something here. If we use this, that is a phase or a line value, is 45.04 amps in a line value. Line value, there's two values that make that up, so it's got to be root 3 smaller. So we divide that by 1.732, and we get, 26.006 amps in the line. So 26.006 amps. So we take our line value of load number 2 and we stick it there. We take our line value of load number 1, stick it there. We take the difference between the two of those, which, so 60.04, subtract 15, and that equals 45.04 amps. That is a line value because we're using line values to calculate it, and then we have to bring it into phase value. So 45.04 divided by root 3 gives us our value of 26.006. I do apologize for that. So now that we're past that, what I was going to say and what I wanted to show you is that if we take these values and we go to calculate what our total power is, our reactive power, and we do 208 volts times 26.006 amps times 3. If we do that, 208 times 26.006 times 3, we get a value of 16.228 kVARs. And obviously we know it was more capacitive, so that would be bar C. But if we look at that value and then we look at these two values for load number 1 and load number 2, if you look at that, you can see right now that if I took the values the way they are, right, because when we calculate powers for phase values and powers for line values slightly different, but they both should come out with the same answer. So if I take my load number 2, my capacitive load, 21.632, and subtract it from 5.4 kVARs, it should give us this value. And we can also plot that as well. We can plot that as 21.632 kVARs and 5.4 kVARs, and we can take the difference between those two, and that difference is what we see here of 16.22 kVARs. Okay, so hopefully that makes a little bit of sense for you guys, and I didn't confuse you too much. So I'm going to get rid of all this. I'm going to do one more all the way through. I'll try to catch that mistake that I made last time. So we're going to do Y for our supply. And Y for our second load. Let's just make this 100 volts here, and we know that those in some way are connected. I'll try and clean up a little bit, and we'll make this as 10 ohms per phase, and we'll make this one 20 ohms per phase. So we have E phase, I phase, and our power. E phase, I phase, resistance, and power. E phase, I phase, resistance, and power. Okay. So, starting this out, we start out the same way as we would with all the other ones. We've got 100 volts in Y. We know that the load that's in Y is also 100 volts. When we come out into the line values, we know that the line values are √3 larger than 100 volts. So 100 times √3, or 1.732, and we would see that we have a value, when we multiply that out, of 173.2 volts. We have an ohmic value of 10 ohms. And so if we did Ohm's law, I is equal to 173.2 volts divided by 10 ohms. We're going to find that we have a current on here of 17.32 amps. So 17.32 amps. And we had 100 volts over here and 20 ohms. And if we did Ohm's law again, I is equal to 100 ohms, or sorry, there should be volts listed there. Volts, 100 volts divided by 20 ohms, we get a current of 5 amps in Y, so 5 amps. So if we calculate our total power for both of these, for this one here, we know that the formula power for reactive power is E phase times I phase times 3. So 100 times 5 times 3, and that should give you an answer of 1.5 kVars, and that's drew my picture wrong on this one. It should be capacitive. Okay, so that's how that should be there. Alright, so 1.5 kVars. When we come over to this one here, we have 173.2 volts per phase. My current is 17.32 amps, and if we end up doing the same thing, we have 173.2 volts times 17.32 amps times 3. You can see that at the bottom there. We have 173.2 times 17.32 times 3 gives us an answer of 8.999 kVars. So that one was capacitive, this one's inductive. And now from these formulas, we want to bring them over here. We need to plot them in a vector. Let me move that just a little bit. Plot that in a vector. Graph her out here. So for our powers, we obviously don't have a resistive portion to this. The larger of the two is our inductive. Our inductive is down here, capacitive up top. We have 8.999 kVARs inductive, 1.5 kVARs capacitive, and if we subtract those two from each other, it should be just under 7.5. So 7.499 kVARs capacitive. So now if we look at our current, the current in Y, that Y of value of 5 in the phase is going to be 5 amps. If we follow that into our line value, it stays as 5. So at that terminal, we have 5 amps. In delta, we had 17.32 amps per phase. So it's both of these phases use up that current. So we know that it has to be, or see that current, so it needs to be root 3 larger. So if we take that value of 17.32 and we multiply that by 1.732, we get a value of 29.998 amps, or roughly, basically 30 amps at that point. But this is inductive, this one is capacitive. If we go to plot that over on this side, as long as everyone can see it over there, inductive we have 29.998 amps, and capacitive we have 5 amps. We take the difference of that, and so we would have a combined total of 25.998 amps. And if we are to do the math on that, if I take 7.499 kVARs and I work backwards, divide by 100, divide by 3, yeah, I get, actually that should be not 25, 24, perfect. And all I did with that when I was working backwards again is we use that formula, but we know that we have 7.499 kVARs for our total power, and that is equal to my volts, 100 volts, times my current, IP, which I do know, but I don't at this point, going the other way, times 3. And I want to isolate all that over to one side, so I divide by 100 volts on one side times 3, divided by 100 volts times 3, and so the formula ends up being IP is equal to 7.499 kVARs divided by 100 times 3, and we get 24.998 amps. So hopefully that works out, and we could use this value here of the 24.998 amps as a phase value, because in Y the phase value and the line value are the same. So this line value, which would have come from there, would have given us 24.998 amps here, and also 24.998 amps right there. Okay, so hopefully that wasn't too much of a head scratcher. I'm now going to write one more of these out for you guys, and you can work on it yourself. So you can pause it and work on it. And then I'm just going to give you one that has just a resistive and a inductive value to it. All right, so let's do 347 volts here. We'll have an inductor as 15 ohms, and we'll have the capacitor as 20 ohms. Okay, so pause the video and work through that. I'm going to take this one up in the next class, just so that you can work through it yourself. Remember, when you're going through to calculate current this way, that you need to figure out, and that was the flub that I had, is that you use your line current for your load 2, line current for your line 1, plot it, get that current, and that value is your line current, not a phase current when you go to calculate it out. But then to double check, you can always go and use your powers on the way back. Okay, so pause that and work through that. Okay, so I'm going to do one with a resistive and an inductive. Let's do a capacitive load. So we're going to do delta. And we're going to do let's do as we said, capacitive in Y, and we're going to do a resistive value right. So these are obviously all connected together, as we had talked about. This is going to be 208 volts per phase. We're going to use, let's do 30 ohms per phase of capacitive reactance, and we'll do 20 ohms of resistance. So this one isn't much different than what we had talked about before, and then there are questions that I've put on Finch Online, and also Dalmar's goes through it fairly well. E phase, I phase, power, E phase, I phase, and our power is going to be in volt amps in this case. So this one is actually, we can say it is parent power. I phase, I guess I got resistance in there, resistance and power. So this is our reactive power, that's true power, and that is apparent power in the end. Alright, 208 volts in our supply. This is load 1 and load 2. And so 208 volts, when we look in the line, is also going to be 208 volts. When we get to the Y connected load, we're going to be root 3 smaller, because 2 capacitive loads are using that current. So we're going to see root 3 smaller, which is 120 volts. Now we look at load number 2. We've got 208 volts in the line, which means also that we have 208 volts in the phase, because they're both in delta and only one load ends up seeing that voltage across it, not 2 having to split it. So we have 208 volts. Now let's look at our currents. If we use Ohm's law, 120 volts divided by 30 ohms gives us a current of 40 amps. So we've got 40 amps here. That was 30 ohms. And in our load number 2, which is a resistive value, we're looking at the same thing, where we do 208 volts divided by 20, so that should be 14, I believe, amps. No, that should be, I think, 10.4 amps. Let me just double check that, although I believe that is right. So 208 divided by 20, yeah, 10.4 amps from 20 ohms. Okay, so fairly straightforward right now. Now we're going to look at our resistive powers. Resistive power, when we go to look at this, we know that P is equal to E phase times I phase times 3. 208 volts times 10.4 times 3 gives us a value of 6.48. Actually, that would round up to 49 kilowatts. Our reactive power, our VARs for our capacitive load, we're going to do the same thing, but we're going to do 120 volts times 40 times 3. We get an answer of 14.4 kVARs. The issue is when we go to combine these now, we can't just add them or subtract them like we did with our reactive power or what we did with our true power. We actually do need to fully plot them out, and we know that this is our, when we look at power, this is our true power here, this is our inductive power down here, this is our capacitive power. So our resistive power is 6.49 kilowatts. Our capacitive power is 14.4 kVARs, and so that's our capacitive value is up and down, vertical, our resistive is horizontal, and the hypotenuse of that is going to give us our apparent power in this case. So if you remember, when you go to find the hypotenuse, it's a squared plus b squared is equal to c squared. So if I take 6.49 kilowatts squared plus 14.4 kVARs squared. So if I do that, 6.49 squared plus 14.4 kVARs squared, and then if I, so that gives us a value, and I'll write that up here, of 249.4801 thousand. And then if I find the square root of, I'm trying to do this on my phone unfortunately, 249.4801 gives us a value of 15.795 kVA. So that is 15.795 kVA as our apparent power in the circuit. So I can do the same thing with the graph and Pythagorean theorem. When it comes to the current, and I just drop that. So when it comes to the current, or I can plug it in and divide it out, but let's just do the current on these. So we need to use line currents here. So line current here, if we had 10.4 amps as our phase current, and we go to look at what our line current was, we have 10.4 times root 3, and we get 18.013. So here we get 18.013. We know 40 amps is going to remain the same because our phase current and line current are going to be the same. So we end up plotting that out, and we get 18.013 amps for a resistive current. Our capacitive current is 40 amps. And now we need to find what the hypotenuse is, and this will give us our total current. So if I work backwards here, so I've got that 18.013 squared plus 40 squared, and my phone doesn't like me. So that value equaled 1,924.46, and I need to take the square root of that. So the square root of that is 1924.46, and I get a value of roughly 43.87 amps for my hypotenuse. So 43.87 amps for the hypotenuse. And then you can also go the other way and take the 15.795 kVARs and divide that by 208 divided by 3, and it should give you the same amount. I'm just going to pound that out quick just to make sure. So 15,795 divided by 208 divided by and then I just did it again. That 43.87 amps is our line current. And I just checked myself again, doing it backwards. It needs to be root 3 smaller. So you need to take your 43.87 amps and divide that by root 3. I'm having a lovely brain fart day. We all get those. Divided by 1.732 or root 3, and we get 25.33 amps. So if you do it around that way, you will double check yourself. Yeah, so always remember that that value you calculate is a line value, and then you need to find the phase value from there. So because of my my lovely brain farting as much as it is, I'm going to end that there, and I will post this. But if you could just go through that a couple more times and not make that mistake, or make a memory aid, mental aid of that, not to do what I did, and you should be good. Okay, have a good day, and I'll see you in the next class. Bye.